Hello, family. This is Can You Do 47, computer output. This Can You Do includes a lot of review because for computer output, we didn't really learn any new concepts or ideas. We learned where to find the information that we can use from the computer output. So we focused on 4 numbers and the part of the output that tells us what the x variable is. So just as a reminder, our 4 numbers are the 2 under coefficient, the s value, and the r squared value. Then this word right here, this distress word, tells us what our x variable is. That is what we covered on or in the lesson for computer output, and then we are applying that information in this Can You Do. I'm not going to spend too much time on 1 and 2 because for most everybody we went over parts of them in class. So where I could, I wrote down what page in our notes you would refer to get help if you didn't remember some of these things. I think it's all pretty straightforward. You have your regression line. Make sure you always define your variables. This asks you to predict y given an x. This is asking about the amount or percent of variation that is accounted for or explained by the linear relationship between the 2 variables. So one thing that I added here in red is that whenever you see the word variation or you see explained by or accounted for, that's usually always referring to r squared. Those are some key words that would indicate to you that they are asking about r squared. So as we are preparing for our exam 4, it's really important that we start noting these things. So words like variation, explained by, or accounted for are always indicating the r squared value. Part D, we calculate our correlation coefficient. So the correlation is a very, well, maybe not very strong, but a strong correlation at 0.878. And lastly, we interpret our value of S. Remember, we can think about S as our typical prediction error, by about how much are we off when we make a prediction using our line. So our predictions will typically be off by about 0.025 units. And I just wrote the word units here because the problem didn't really specify what the units are, if there are any. So our predictions will typically be off by about 0.025 units from the actual brain activity when we use the LSRL. Number 2 is a problem about magazine publishing. We did this in class for, I think it was my A day, and the answer that I got on one of these is wrong. So maybe just look through this and double check. If you don't want to watch the solution, just double check that your answers are the same as mine. A asks for the slope and the interpretation. So for every 1 year, our model predicts magazines published will increase by about 325 magazines. What is the y-intercept? And interpret. So in or during 1988, which was year 0, our model predicts that the number of magazines published will be about 13,550. So this is the one where I did it wrong. It says predict the number of magazines published in the United States in 1999. And I plugged in 1999 for the X value and got 664,000 magazines, which didn't really seem unreasonable to me. Like, in all of the United States. It didn't seem crazy to me that there would be that many magazines. But now that I think about it, I realize that that number is actually very high and probably doesn't make sense. What we were supposed to plug in instead of 1999 was 11. The reason why we're supposed to do that is because they tell us that 1998 is year zero, which means if we were going to predict for 1988, we would plug in a zero. If we wanted to predict for 1989, we would plug in 1. If we wanted to predict for 1990, we would plug in 2. So if we're predicting for 1999, that's 11 years. So 11 years from 1988, there were about 17,000 magazines published. That seems a little bit more reasonable. So be careful on that, guy. There's not anything like that on the unit test that I'm giving you, but it is important that you note that sometimes that happens, and I have to be a little bit more careful about what value they want me to plug in. Okay, find R and interpret. So there is there is a strong positive linear association between the year since 1988 and the number of magazines published. In general, as the year increases, the number of magazines published also increases. Interpret R squared. I need to put the word about here. About 84.8% of the variation in number of magazines published can be explained by the year when using the LSRL. You don't have to put the word about there, but I like to put it just to be as accurate as possible. This is not wrong. I just think that I like to say about 85% instead of leaving it off. Okay, the Da Vinci problem is the one that I figured that I would spend the most time on. I would make sure that you really understand and know how to do this problem. Hint. Let me say that again. It is very important that you understand and know how to do this problem. Okay, so I mentioned this in class, and I'm going to mention it again. The reason that I included this in your Can You Do is because I was shook at the amount of students who got this wrong last year on this unit exam. So I felt like if that many students were unable to answer this question, then it's definitely worth one looking at a little more in depth. So the setup is that Leonardo da Vinci speculated that an ideal human would have an arm span that was equal to their height. So arm span is this distance from longest finger to longest finger. He's saying that an ideal human, their height would be the same as their arm span. The regression output, or the regression printout, shows the results of regression run on a sample of 18 high school students. Now it wants you to go through and see which of these answers is false. Which of these is false? Which means where you can, you really should check it using calculations or definitions because you have your notes at your disposal. So let's make sure that we really understand the setup before we get into deciding whether each component is true or false. So the first thing that we are going to want to make sure that we feel really good about is our x and y variable. X equals, y equals. They don't really tell us in the prompt what x is, but we know from the computer output, because it gives it to us, that the x is going to be height, which means the y is going to be arm span. Okay? Well, let's talk about the equations then, because we have two different ones. We have what Da Vinci thinks, and then we have what we observed from the 18 high school students. So Da Vinci thinks that height equals arm span, or vice versa. Arm span equals height. The ideal human has an arm span and a height that are the same. That means that Da Vinci thinks y equals x. Our high school students, however, provide us with different information. So the high school students did not result in an equation where y equals x. The high school students produced an equation that looks like y hat equals, and now we go up to our computer output, 11.5474 plus 0.84024x. So Da Vinci's claim, the equation that the actual data gives us. So Da Vinci high school students. Now this is enough to get us started checking answers. So the least squares regression model, okay? Well, let's make sure that we know which one of these is the least squared regression model. Hopefully you're thinking, well, duh, teacher. It's definitely this one. The least squares regression model will make a prediction that is 1.64 inches higher than Da Vinci's projected for a 62-inch tall student. So A, x is 62. Okay. Well, according to Da Vinci, what this would mean is that y is then 62. Because Da Vinci says y equals x. For our high school students, we actually need to plug that in. So we plug in 11.57, just kidding, 5474 plus 0.84024, plug in the 62. If you plug that into your calculator, you get 6364228. Okay, well, what is the difference between the high school's prediction and Da Vinci? Well, it's higher. Higher by how much? To find out, we would do 6364228 subtract 62, which gives us a difference of 1.64228. So now let's go back up to part A. The LSRL would make a prediction that is 1.64 inches higher than Da Vinci's. True. A is true. Our prediction of 63.64 is 1.64 inches higher than Da Vinci's height would have been. Well, not his personal height, but his equation's height. KB. If one of the students in the sample had a height of 70.5 inches, okay, height 70.5, that's X. and an arm span of 68 inches. That is Y. So we have a student, an actual student, with this combination of height and arm span. Then the residual for this student would be negative 2.78. Okay, so I'm hoping you guys remember that when you calculate residual, I always set up 4 things: X, Y, Y hat, residual. I have X and Y, I can calculate Y hat by plugging in 70.5. So 115474 plus 084024, you're plugging in 70.5. So one thing that I cannot stress enough about problems like this in this unit, write down all of your information. I beg you, write your information down, because it's very easy to accidentally plug in 68. They give you X, you plug in X. You want to keep things as organized as possible. This predicts a height of 70.77. So the residual is the actual subtract the predicted. So 70.5. Just kidding, I did that wrong. Do you guys know what's wrong about that? This is X. I needed to write down Y. So Y was 68. I'm going to highlight that so that I don't make that mistake again. Y minus Y hat of 70.77. I think I may have rounded that wrong. I think I rounded that guy wrong. I don't have my calculator next to me. This would give me a negative 2.77. The option says the residual for this student is negative 278. I got negative 277. I'm pretty sure that I rounded that wrong. So B is true. So far, true. True. C. The least squares regression line has a steeper slope than the equation for Da Vinci's relationship. Okay, so LSRL has a slope that equals 0.8424. Oh, I forgot a 0 in there. 0.84024. How do I know that? Because look at the line. This is slope. So knowing that this number next to X is the slope for the LSRL, what is the slope for Da Vinci? So this is the slope for the LSRL. What is the slope for Da Vinci? Da Vinci's slope is 1. As height increases by 1 inch, arm span increases by 1 inch. So slope is 1. Here, slope is 0.84. Which one is steeper? Da Vinci's. 1 is bigger than 0.84. $1 is more than 84 cents. So Da Vinci's slope is steeper than the LSRL. So C is false. What if, though, you didn't know how to do or check C? You knew how to check A and B, but not C. Then check the other ones and see if they are true. So you go, I don't even know about C. So look at D. For every 1 inch increase in height, the regression model predicts a 0.84 inch increase in arm span. Yes, this is just the definition of slope. For every 1 increase in X, what does Y do? So in this case, for every 1 increase in height, arm span increases by 0.84 inches. E, for a student that is, so this guy was true, sorry. For a student 66 inches tall, our model would predict an arm span of about 67 inches. So for E, you would just plug that in. So E is 1, 1, and all of a sudden, I don't know why, but I started rounding. Who knows? 1155 plus 0.84. You are plugging in 66. This would give you 66.99, which is approximately 67. So this is true. So if you didn't know how to check C, you could deduce by process of elimination that the answer is C, even if you were like, I have no idea what the line for Da Vinci would be. You could do this whole problem without ever having to write down y equals x. You would just need to know that Da Vinci thinks that they are equal. Okay, so I know that that was a longer explanation, but I do think that that explanation is worthwhile and important for you to, this problem is really important for you to understand. If you're feeling good about this problem, then you're probably on the right track for what you need to know for this unit. Okay, I think after this we have one more problem. So it is the fish in the different temperatures, and I believe that it is 2 multiple choice questions. So scientists examined the activity level of 7 fish at different temperatures. Fish activity was rated on a scale of 0 to 100, the temperature measured in Celsius. The computer printout and the residual plot are below. Okay, so what is the activity level rating for the fish at a temperature of 20 degrees Celsius? So for me, the most important thing is to determine, before I start this problem, the most important thing is to determine what is x and what is y. So what is my x variable? What is my y variable? I like to go to the computer output to help me. So x is your temperature, which means y has to be your activity level. Okay. So what was the activity level rating for a fish at a temperature of 20? All right, well, that means that x is 20. Okay, well, they're asking me then about y. They want to know what y was. Okay. So I know that I can find this by using the formula for a residual. So I can calculate y hat. I have to use the regression equation. So that regression equation is 14862 subtract 3.22x. I'm getting that from my computer output up here. So to find predicted y, 14862 minus 3.22, you're plugging in 20. That gives us 84,826. Let's make sure that we are clear on the fact that x is 20. We plug in 20 for x. Okay, so then the last piece of information we need is the residual, but they didn't give us the residual in the prompt. However, we can find the residual from the residual plot. So we're looking at a pause. We're looking at a residual plot, but they told us something that was really important in our explanation of the graph. They say, notice that the horizontal axis is labeled as fitted value. That means that this horizontal axis is y hat. It's all the y hats. So what this is giving you is your predicted y value and the residual that matches your predicted y value. So this fitted value is the same thing as predicted y or y hat. We have a y hat of 84,826, so essentially 85. So we're going to come to the y hat of 85, and we're going to find its residual. So we're going to just follow the graph up to where the point is, and then we can follow the graph over to the residual it matches. So our residual is 2.5. Our residual is 2.5. Okay, now we can use the formula. So I'm going to do that down here. We get residual is y subtract y hat. So 2.5 is equal to y subtract 84826. To solve this, you would add 84826 to both sides. And we get that the actual activity rating is, I didn't add it, Famil, 2.5 plus 84826, 87,326. So about 87. So the answer to this one is A. The answer to this one is A. So biggest takeaway from this one is recognizing that you could use the residual formula, and then knowing that what this residual plot is giving you is your fitted value, so your y hat, and its matching residual. So a y hat that was 55 would have a matching residual of like -4. Okay, last question, 5. Which of the following gives a correct interpretation of S in this setting? It is C. I will walk you through all of these options. For every 1 degree increase in temp, fish activity is predicted to increase by 4,785. This is slope. And how I was able to quickly identify that this is slope is this starting phrase for every 1 degree increase. B, the typical distance of temperature readings from their mean is about 4,785. So this is the standard deviation of X. X is temperature, and this is saying that the typical distance of the X value from the mean is 4.785. This is standard deviation of the X variable. The typical distance of the activity level ratings from the least squares regression line is 4,785. That sounds about right. It's not exactly the same as our definition or our interpretation or sentence frames, but it's pretty close. D, the typical distance of the activity level readings from their mean is 4,785. This is describing standard deviation of Y. And then lastly, at a temperature of 0 degrees Celsius, this model predicts this is y-intercept. How do I know? Because X is 0. This problem is also a really good problem to use to assess where you're at with this unit. So, for sure, you should feel good about A and E. So you should feel comfortable with the fact that A was slope or is slope and E is y-intercept, and comfortable with the idea that for every 1 indicates slope and at a x of 0 indicates y-intercept. B and D are a little bit more complicated, but if you remember the definition of standard deviation, it is the average distance from the mean. So in this case, it is the average distance from the mean for the X variable and the average distance from the mean for the Y variable. So I know that because it says typical distance of the temperature, typical distance of the activity level. So temperature was X, activity level is Y. You saw this standard deviation of X, standard deviation of Y in this lesson. Right here, you use S of X and S of Y to calculate your LSRO. So it would have to be this one. And what this is saying is it's the typical distance from the line, which is the same thing as what our sentence frames is, which is the typical distance from the actual value. Okay, so this was a lot longer than I intended, but hopefully it helps. One of my students told me yesterday, I was watching one of the videos for the next stats unit. I was watching the videos on the AP board, and the lady that was doing the lesson was talking so slow, and I'm like, this lady, and one of my students was like, oh, just turn up the speed. Mind blown. My whole life changed. I didn't know that you could turn up the speed on your videos. So hopefully you watched this at 1.5 speed if you needed to, and this only took you 15 minutes instead of 35. Regardless, hopefully you're just watching what you need on these. Make sure, like I said, that you feel really good about this problem, this fish problem, and the Da Vinci problem. Make sure that you feel good about the fish problem and the Da Vinci problem. They are great problems for assessing where you're at on this unit. Okay, love you guys. Any questions, email me, and I will get back to you ASAP.